Hello everyone, this is Luboš Pirkl from CFD Support. I would like to welcome you to the webinar where we would like to talk about centrifugal compressors, how we simulate them using CFD and other simulation methods. So the topic is centrifugal compressor, and which is the background of showing what we are doing here every time, all the time for last 15 years, which is CFD software called TCAE, and we will show our tips and tricks and our visions how we think such things like centrifugal compressors can be simulated and tested and optimized potentially. So I hope all the techniques is working well, and we will make a good webinar. So, well, a couple of notes in the beginning. So as usual, the webinar is being recorded, and its recording will be later made publicly available on our YouTube channel, and the link to it will be sent to everyone who attended. So that's this. There will be, at the end of the webinar, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions and we'll be happy to answer all of them. The most representative questions will be answered right away in the webinar. The specific questions will be answered later via email, but you can be sure that all the questions will be answered. That's this. Yeah, and a little notice, please ask anytime during the webinar. There's a special window in the GoToWebinar client, so you can ask your questions all the time before you forget what you wanted to ask. Ask as many questions as they pop up, and we'll be happy to answer them. We all want to avoid let's say awkward silence at the end of the webinar where we can't see any representative questions. So don't let us in this alone. Okay, so this is me, Luboš Pirkl, and together with me on the line is the real expert on simulation, which is my colleague Radek Máca. Let's check the connection. Hello, Radek.
Yeah, hello, Luboš, and hello to the audience. Hello.
Can you see us? Can you hear us?
Yes, I can see you. I can see your screen. I can hear you.
That's
so I
great.
hope also the audience can hear us and see us.
Okay. Anyway, okay. Yeah. So there will be like 3 parts of the webinar. I will start with the necessary information we have to say because we make this business for living, and that's the software. So I'll tell a few necessary notes about it, but don't worry, I'm not gonna torture you more than it's necessary. Then in the second part, Radek will introduce a workflow, how we approach to it, and you will get the feeling how we do things. You will learn how we simulate compressors. And in the last part, there will be Q&A session where we can answer our questions. So sit down, make yourself comfortable, grab a cup of coffee and enjoy, and we will slowly start. So I will recommend that we would switch the cameras off, Radek. Right? We will come back. We are still here. We are running live, still here all the time. But we will switch the cameras off because we believe that the ratio of information is so much better if we are only in the background. Yes. Okay. So still, before the end of the year, there will be couple of other webinars. Just briefly, in 2 weeks, a webinar on Francis turbine. Another 2 weeks, airfoil acoustics and possible optimization with serrations. Another great topic. Somewhere around that time we will release the new version. So about at the end of October and in the beginning of November, there will be another webinar where we present all the new features, etc., and news. And news are coming all the time. We are working all the time and developing 24/7. So yeah. There will be also a webinar about wind turbines in this in November 26, and the last webinar of this year, I think it's blood pump benchmark, which will be on December 10. Okay, so a couple of webinars to go, and the introductory part starts now. Basically, the company is called CFD Support. That's us. We work from here, from Prague, Czech Republic, and we do quite a lot of things related to CAE simulations, and yep. We develop software. Mainly, we do quite a lot of consultancy business, but I would say that our main business, our primary business is software called TCAE. There are a lot of things we could say about it. It definitely consists of modules. There are modules for meshing, modules for CFD, for FEA, for acoustics, for optimization, and more. So all the time, more modules are still to come. And TCAE is extremely flexible. It's ready to fit any existing workflow or any completely new workflow from scratch. It works perfectly with existing commercial codes, in-house codes, with other open source. It's ready to fit. You can use it in very wide range of ways. So it's very flexible. The license of the software is unlimited, so there are no limitations on number of users, jobs, or cores. There are no limitations on hardware installations, and users can use their resources to the fullest. It's accurate. It's focused on turbomachinery applications and on external aerodynamics. It's automated, and that's for that reason it's extremely effective. We for like last 15 years we are gathering very politely all the data and benchmarks, and we did a lot of them, and quite a few of them are available publicly. Those we were allowed to make public are available. So it's proven software. We have good technical support. TCAE can be used in very wide range of in all the spectrum of using CFD and simulations. That means you can use it remotely, you can use it on laptop, you can use it on a small scale or in big scale on a cluster cloud, or remotely you can work from on it directly from another computer. It can be used in Windows, in Linux. You can use it in many ways. And the important point is that the workflow is same everywhere. So in Linux, in Linux, in Windows, still the same software. So you can for example prepare, make the tests and preparations in Windows, and then productive simulations run in Linux, or the other way around. It's completely flexible in terms of usage. An important point is that it's completely based on open source. So we have mastered the process of acquiring open source codes or code and make out of it a professional CFD code which is usable in the industry. That's very important. And what's also very important, on top of all the open source that are used, we've spent more than 50 many years in development in a team, consistently making it better and better to be usable in the industry. So imagine how much work has been spent on the open sources which are used, and on top of it we've spent 50 many years, aggregated of course, of team development to make it happen. So it's really a lot of knowledge and experience and skills is included in it. So that's just a little example, and we continually developing it. So the new version is just around the corner. We will release it in about 2 weeks, and there will be a couple of news. And if I should mention a little bit about the future of software, so we will definitely keep developing optimization module. So optimization is a huge trend. It's really a really big thing. So the optimization module will be developed. The acoustics module will be further developed because we have quite a lot of success in this area. So acoustic module is being developed very heavily. New module will be T-based, so the users we will allow our users to create their own surrogate models based on their previous results. So no result will be ever left behind. So everything will be possible to store in large databases where the data will allow us to use machine learning, and based on them, users will be able to create their own surrogate models based on their own research and results. That's quite big thing. And also we will make a big announcement with the new version. There will be a light version of our software. So there will be TCAE light version, which will be accessible to literally everyone. Everyone will have a chance to use TCAE light. We will make it in a way which is accessible to everyone. So definitely a new light version will be available, and we are definitely looking forward to it so much. Okay, so the new version will come soon, and still we will talk about what's already available, which is the version 24.03. And I think now it's time that we will ask Radek. Radek, still with us?
Yes, I'm still here.
That's perfect.
And ready for my part. Okay.
Yes,
Okay.
that's great. So I have just passed the presentation over to you, and now we can see your screen. So the stage is yours.
Okay, perfect. Thank you, Luboš. And I will jump into the compressor topic. And today we will look at the compressor case, and we will show how the workflow works and of which part it consists. So let's go to that. And because we are talking today about the compressor, so I try to compress all the information into the shortest possible time frame. So let's go for it. So let me start on our web pages. So if you go on our web pages, you can find all the tutorials, and one of the tutorial is this one. On our web page, you can also chat with our virtual versions of us. So you can chat with the chatbot. But I would like to go to the case studies, and here in the case studies, you will find all the available tutorials which you can directly try on your own. And one of the compressor, we have this HECC, which is the, I think, more complex case. It is part of a benchmark. So this is very nice example of compressor application. But we will go to the older one case, which is the radial compressor or centrifugal compressor. So you can download it right here, and let's check this compressor.
By the way, Radek, can I interrupt a little bit?
Yeah, sure.
Do you think the chatbot window is too annoying? Maybe shall we not let it to pop up all the time?
Yeah,
What
maybe it will be a good feature. Just
now,
pop up for the first
now when
access.
I see it, it's like, okay. Anyway, sorry for the interruption. I'll do my best. Yeah.
Okay, good. So we are testing all the time, everything.
Improving all the time.
And improving, of course. Okay, so here you can download the case and read some details about it, and we will work with this particular case, which goes along with us for more than 5 years, I think. So it's one of the first tutorial for the Turbomachinery we delivered to the public. So let me jump back on the disk, and here I have downloaded downloaded it, and I will open it. And before the training or before the tutorial, I already ran one of them to see how it behaves live, what you can do during the simulation. But let's postpone this to the end of my part. So if you have downloaded the case, you can directly open it by TCAE, and because I have many versions of TCAE here for testing, so I will open the latest release, so 24.03. So I will go to my desktop where you can see all our team on vacation. But anyway, I will open TCAE 24.03. So let me open it. So here I have a new GUI, and by clicking the load button, I can load any case, or I can start from the scratch, but it will take much more time to create, of course, the project from the scratch, but you can do it here by create empty, or you can copy setup of the existing project. But here I will just load one of the downloaded radial compressor example. So let me do it. Now the project is loading, and after the project is loaded, you can see all the setup, you can visualize the input geometry, etc. So this is how the GUI looks like at the beginning. So the render view is split into the several parts. Here we have the input geometry rendering. Here we have kind of line chart view to visualize the residuals or an integral quantity during the simulation. And at the end, we can see here the final reports of given module which is finished. So for example, we can see the TCFD report and all the relevant information presented in the report. So the first of all, if you starting with the project, you need to have the geometry, and the geometry must be ready for CFD simulation. So it means if you start from the geometry, then you need to import the STLs in this case, and the STL or STLs has to describe the flow path of your machine, in this case centrifugal compressor geometry. The setup consists of, or the topology of the geometry consists of several components, or can consist several components. For the turbomachinery, always needs to have at least two components, because for turbomachinery typically you have a rotating part and non-rotating part. So typically a rotor is set as a separate component, and stators are also set as separate component, because then we can easily set all the all the necessities in the background. Automatically it will pick up all the cells within the rotating region to prescribe rotating motion or the physics behind, etc. So this makes the workflow more simpler and more modular, which is simpler to understand the whole process. So here we have four components because of the topology of this compressor. So we have the impeller, the rotor part. Then we have two diffusers because of some topology of the software from which this was exported. I think it was from CF Turbo from 5 years ago, but I think the principle is still the same, or the topology is very similar up to date. And then we have a volute. So for example, for those who are CFD experts, or who work with CFD on daily basis, it can have a node that, for example, the inlet and outlets are too short, because when we set the inlet condition right here, which is typically some total pressure condition or volumetric flow rate condition, which in the easiest way is set as perpendicular shapes. So typically the flow goes perpendicular to the inlet patch, if not set in another way. But in this case, we have the total pressure inlet, so we can see that, okay, it's too it's too close to the rotating part, so the physics or the real flow at this part is not perpendicular. It starts to rotate right near in some neighborhood of or in front of the impeller. So for example, as an example, we would like to define some inlet extension to this shape, because I don't know the diameters exactly of this geometry, which you typically know when you do the project on your own geometry. So let me just check. So if I go to the multi-block inspector, and for example, I can just pick up the rotor inflow, and if I go now, if I check it, go to the information, then we can see some dimensions of this. So the outer diameter, if I click on the inflow, so the inlet diameter is 33 millimeters. The position of the inlet flow rate is at the z coordinate 0. And if I would like to check the inner radius, so let me go here. Here we can choose this hover point, and we can check, for example, one of these coordinates. So it's something like, yeah, the maximum y coordinate. So 6 millimeters is the inner radius. So knowing these values, we can quickly create geometry which will correspond to the inlet extension of this part. So for this purpose, you can choose any CAD software. So we typically use Salome because we love open source software, so or free to use softwares. So we typically use the Salome or any other CAD software or tools. So let me go to creating the new inlet extension. So here, because I would like to create the extension in, I think it is in, if I again check everything, in the minus z direction. Yeah, so typical. So I would like to create some cylinder which start at the 0 coordinate for the z axis and goes in the minus z direction. So I will create a new vector which points to the minus z direction. So I will create by this option. So minus z vector, for example, I can call it. Now I can create a cylinder. I will create cylinder based on the base point. So it starts at origin and goes in the minus z direction. The radius was 33 millimeters. Okay, and the length depends on our experience. So let me, okay, sorry, I unclick this vector direction. So let me do it. For example, the 20 centimeters will be, the cylinder length will be 20 centimeters. Okay, so this is the outer radius. Then I would like to do the inner radius. So I can, for example, create the inner cylinder, but for example, I would like to create some kind of hub region, some artificial or the exact shape if I have the original geometry. So let me, for example, create a sphere of the radius of the inner size radius for my original inlet, and it was 6 millimeters. Okay, was it true? Sorry. Let me just double check this. So I think, okay, it was the radius. Sorry. So let's go back. So the cylinder is too large. So again, was not the diameter but the radius. So the radius was the 20 half of 43, so it's 21.5, and the height will be 200, let's say. And okay, and again switch to the direction. So again, this one, and the base point and the direction again, right? And now I have the proper sizing. And because I would like to cut off this part to have a geometry, so I can do a simple operation, Boolean operation, and I will choose the cut. So I will cut off the sphere part from the cylinder. So check this one. okay, and I have a nice shape here. Now I need to do the splitting. So because I would like to export several parts separately. So this will be the new outflow from this extension. This will be inflow. This will be the hub, let's say, and this will be the wall for the extension. So to do that here, I can create a group on it, and this group will be then copied into the exporting STLs. So I would like to do the group on the faces. So let me start. So this face will be the inlet. This face will be the outlet. Apply. This inner half of the sphere will be the hub. And last but not least, the piping wall will be just wall or wall extension. Doesn't matter. Okay, so depends up to you. Okay, so we have all these parts, and then to create, because the STLs is created from the triangulation of the surfaces, so I can create here in the meshing module of Salome. I can create a surface mesh. So let me click here, create new mesh for the cut one. It's okay. I would like to create just the surface meshing. I will use the netgen, and here just type the parameters of the triangulation. So you typically find enough triangulation to have nice and smooth description of your originally smooth continuous shape. So let me try these parameters, 2 millimeters as a maximum and 0.5 millimeter as a minimum. Now we can click here, compute, right? And this is our output from the meshing. So we can see, for example, that the hub is still too rough. So you can also apply some local refinement, but for the ease of use, I will just click, for example, I will use 0.5 and 0.2. Very fine, I can click, and let me compute again. So clear and compute. So now the meshing is generated, but maybe it will be too fine. But let's keep it. You can also manage local refinement, so you can set finer triangulation on a more small and highly curved parts, and rougher triangulation for the bigger and flat parts. But for ease of use, I am fine with this, and now I can export each group which were copied from the CAT module to here, so I can export them separately. So I will go to our working directory, webinar. Here I will create, for example, STL directory, and in which I will put the STLs, and to save some place, I can save it as binary files. Okay, so I will do it for each part. Okay, so hub, and finally the wall extension. Okay, so I have new for STLs, which I can import into my existing project and create the extension to this geometry. So we can go back to the TMesh module. So here each component holds the geometries and mesh parameters for each component. So I can add a new one, new component 5. I can name it as inlet extension, and now I can import surface geometries. What I haven't mentioned yet, that you can also import the existing or existing volumetric mesh which is ready for CFD applications, and the provided formats are the OpenFlow mesh, Fluent mesh, MSH mesh, and CGNS mesh format. So you can import if you have your own mesh generator, or if you have any software which can give you meshing, so then you can export it into the proper format and load it into the TCAE. But here we have the surface geometries. So I will locate the STLs and I will load all the STLs. So I hope my dimensions was correct. Yeah, it fits good, perfect. So we have this extension. And now we can show how to set up the meshing for the component, and then the rest is basically the same or very similar. So let's start. Here we have the reference frame, which means if all the objects or the objects within this component is rotating, physically rotating, so this is applicable for the rotor region. So here we have the static region. Periodic geometries, for example, if you have a geometry which just follows the segment, one segment, periodical segment of your blade, stator, cascade, or rotor blade, then you can apply the periodic geometry to tell the solver that how to treat this component. Okay, so periodic geometry. Then you have this table with all loaded STLs. So first column in this table is the type of the patch. So typically from the CFD world, you have the inlets, outlets, walls, some interfaces, and or some specific geometrical constraints like symmetry, planes, etc. So here we have the hub. So here we can call it as a hub. So this is Turbomachinery specific to better distinguish these shapes if they have some weird names originally. So we can set it as a hub, and the hub is a part of the rotor. So let me just, if I click CFD geometry and I go to the display, I can increase opacity just to see inside. So this part. So if you double click anything, then the double clicked patch will be visualized or highlighted in the render view. So this is the hub, and the hub is physically rotating. So we can, for rotational symmetrical parts, we can adjust also the rotation within the static component. So here we tell that the velocity of the patch will be set with respect to the rotation speed of the rotor. Then inlet, so you need to set the physical inlet into the domain. So this is the inlet. Outlet should be not the outlet, because outlet means that this is really the physical outlet of the from your geometry where the outlet boundary condition is preset. But to connect the outlet to neighboring inlet of neighboring component, there is these types inlet outlet interfaces. So here I can click outlet interface, and wall extension will be the typical wall. Because I have added this part and this was the original inlet, so I need to go to the component 1, to the rotor component, and change the rotor inflow, so the inlet, original inlet, if I double click, to the inlet interface. Yeah, so I need to do this one, and then because the topology can be pretty complex, then I need to explicitly say to which patch or how to connect the components per patch pairs basically. And to just see, yeah, the topology of the connection, you can see it in the components map. So this is just a simple components map which shows you how the components are connected. And we can see that our new component is not yet connected to any component. So we can go back to the T-mesh part, go, for example, to our component 5, and we will connect by right click on the type to the impeller to the rotor inflow. Now we have a nice connection from the inlet, from the new inlet to the outlet from the volute. And similarly, we can create an extension, for example, to the volute part and add a 6th component in the same way. All right, so this was the connection. Reference frame was also set, and now minimum maximum refinement. So here you are setting the mesh refinement, the mesh parameters for your component. It starts from the background mesh cell size. So typically you would like to choose some cell sizing of the neighboring component, because then it makes sense to have a similar refinement on the interface and similar topology of the meshing. So let me check. So we will use this number, or for example twice buffer, because this is just the inlet extension, so I don't need to simulate all the details in the flow. I just would like to let it flow basically. So let me check. So we will use the cube cells, and for example I will set half, double of the sizing for the rotor, so 1.5 millimeters. And just to see the topology, so this is our, let's say, refinement. This is our cell size of level 0. So basically this is the topology of the cells which will be inside the flow domain in the volume. Then we can set the refinement based on the surfaces. So for example, because I would like to fit the interface nicely from both sides, so I can check what is the refinement on the rotor inflow. So there is a level 0, but with a half of the sizing for the background mesh. So to have the same sizing of the cells at the interface, I can set here level 1. You can set different minimum and maximum level, and then the maximum level is typically imposed for the highly curved areas. So if internal engine decides that the curvature is higher than some thresholds, then it applies high level of refinements. So in this case, everywhere will be level 1. Then what we have here is the internal point, because we have object, and we can do either internal flow simulation or external flow simulation. For example, you would like to see the parameters of the cylinder in the external flow regime. So therefore, the meshing engine doesn't know which part to kept for the simulation. So then we need to tell it by this internal point. So you can set it manually, or you can use this show internal point as sphere with radius just to see it in the GUI, and just place this point inside your component. And basically that's all. There are other parameters, but I think we don't need to comment them at this point. So this is done basically for every component, and whenever you are fine with it, you can set number of processor which your computer has. So maybe I will just set 1 for now, because all my CPUs are now used for the simulation. So I will just decrease it to 1 just to show you the example how to create a mesh. So whenever I'm fine with my setup, I can confirm it by clicking on the save button. And now here, if you click to the first item in the pipeline browser, which is the manager we call it, then you can click to mesh each component separately, or you can click on the mesh all button. So let me, for example, check how we set the parameters for the inlet component. So now the mesh generation is ongoing, and if you click here, for example, in this TCAE output section, you will see what is happening at that moment. So this is basically the output of the SnappyX mesh. So it could be very useful for those who are somehow familiar with the Snappy. So this is standard SnappyX mesh output, and in the end, there is the output of the check mesh, let's say, and it will tell you all the parameters about the cells and the quality parameters connected to the generated mesh. All this information are also then printed into the TCAE report. Okay, whenever the meshing is done, I can click on show button to visualize the mesh, so I can get rid of the CFD geometry. So any object which can be visualized can be found in this pipeline browser. So this is the CFD mesh, and the CFD mesh, to see the topology, I can click on the surface with edges, and this is my topology. Okay, for example, the mesh on the hub is too rough, so I can go back, set a high level of refinement for the hub part, which I forgot originally. So wall extension, for the hub, definitely I need to have the final level of refinement. So I will set, for example, 2 to have a nice meshing. And of course, I can add the boundary layers to it. So basically, you just choose how many layers you want. And for detailed parameters about the inflation or boundary layer, you can find in the advanced meshing options in the section of the layers for component 5. And here are the parameters of the layer. Expansion ratio, thickness of, you can choose the sizing of the layers and other parameters. So typically you should take care of these 2 parameters to adjust the sizing of the layers within the inflation layer. Right, and again, if you save, so then the setup is changed. So the original results are deleted, and you have to recompute the meshing. And in this way, you can step by step create your perfect mesh and go for CFD setup. The CFD setup is pretty straightforward. Our workflow is always focused on a particular type within the geometry, within the turbomachinery applications. So here we have several types, and for compressors we have this compressor type, which sets on the background efficiency formulas and other evaluations which are exclusively connected to the compressors. And another standard, I will just mention the time management. For the compressor, typically you would like to have the full efficiency map, but not only for one fixed RPMs, but for several RPMs for which you would like to reveal the efficiency map and performance of your compressor. So you can ask for example, 2 speed lines, and each speed line means that it will simulate the compressor at a constant speed line with different boundary conditions, and this can be set for each speed line. Then, for example, in the boundary conditions, here you set the boundary conditions for each point and for each speed line. So typically, because I have changed the inlet, so I need to redesign the inlet total pressure values. Yeah, so you will click into each box and you put your values. The same for total temperature at the inlet. And because I haven't changed the outlet, so the fixed outlet boundary condition of type outlet vent is kept here. And by going through each menu, you will set standard CFD parameters. So I think you can check one of our previous webinar where this was discussed in more detail. And whenever everything is preset, including meshing and CFD simulation, you can hit Run All button, and everything is run in an automated way. So which brings me to my GUI where I ran it, I think yesterday evening. So this is the GUI and the status of your simulation when the simulation is running. So you can see the mesh was generated, and now we are in the phase of CFD simulation. So we can see now that the first point of the third speed line is calculating. Anytime during the simulation, you can ask for the light or full CFD report. So let me click on full CFD report. Okay, so I need to just click here and click full CFD report. So it will give you information about the current simulation, all the data which are available at the moment. During the simulation, you can watch for the residuals, for example. So if you enable here the residuals, focus on the results. So these are the residuals for the currently running speed line. the same for the quantities. So you can go for quantities. In the display section, you can choose your favorite quantity to watch. So for example, I will go for the efficiency. So if you locate the efficiency, then you can see the efficiency. And here in the view, you can focus the range just between 0 and 1 to see the efficiency, really, actual values and the averaged one. Whenever the report is generated, oh, it's still generating, okay. Okay, it can include some blade-to-blade views, which can be set, some special views for the turbomachinery. So then it will appear here. So all of these can be watched. So let's wait for it. And of course, anytime during the simulation, you can, or after the simulation, you can see the results. So during the simulation, you can click here to view current time step. So I will do it to trigger writing the results and to see actually computed points. And at the end of the simulation, you can simply click on show CFD results and go to visualization of your CFD simulation. So let me wait for this. Maybe I would like to be too fast at the end. So Luboš, if you have any question or comment, just jump me in.
Yes, I would just, sorry, Radek, I would just ask the audience to ask your questions. So we will be definitely happy to answer them. So ask your questions if you like. Use your chance to the fullest. We'll be happy to answer them. That's the only notice from me.
Okay, perfect. So the report is generating. Yeah, the results are now loading into the GUI. But for example, for an example of the CFD report, you can go to our web pages and see how the report looks like for this particular example. So this will also load, and yeah, here the results, the current results are already loaded. So basically you have the time steps evaluated for the speed line. So we have the current results for the current iteration which is running. So you can check visually if your simulation is running well, if all the quantities are converging. So this can be visualized anytime during the simulation. If we wait for the report, but I think there are many render views to be visualized, so it takes some time. So it will take maybe more time than we have. But let's see on the report on our web page. So this is how it looks like. On the first slide, in the first section, you can see nice overview of the performance map. So we have 3 speed lines, 6 points per each speed line. So you will basically see 18 results. So for different flow rates, you have the efficiencies, total pressure difference, and the total pressure ratio. So this is some kind of overview of the compressor simulation. And for each speed line, you have a specific part, specific subsection, which gives you all the details about the simulation. So simulation statistics, what was simulated, sizing of the mesh, the details about the Y+, details about the quality parameters of the mesh, how many cores were used, how long does it take to get the results, so time spent on the processors, and then you have several parts, several sections which introduce the given quantity connected to your machine. So here we have the efficiency for the speedline 1. Here we have the torque. Always there is a couple of graphs. First, the final results and the convergence of your quantity. So here also you can see the quality of the results. You can check axial force, total pressure difference, total pressure ratios, total pressure per interfaces, so you can see how the pressure changes for different conditions and for the given interface, what is happening and where. The same holds for the temperature and many other question sections. And the final part is visualizes the specific turbomachinery visualization. So first one is blade-to-blade view. So this unspent or unwrapped wheel, and then the given slices are presented here with the velocity magnitude and the stream traces. And I think the second one is the meridional average. So meridional averaging of your impeller component, and static pressure is visualized. So you can see the static pressure jump throughout the channel of the impeller. So this was the TCFD report. And okay, maybe I will stop here. I will give the presentation back to Luboš, and maybe during the Q&A session we can go back to see the result, or to answer the question via the GUI or whatever. So maybe Luboš, if you can just to conclude, and then during the Q&A we can go back.
Yes, Radek, that's great. Thank you for your part. It was again very informative, and for me a little surprised that you also entered the deep waters of Salome and adding stuff. So it's definitely what surprised me, and again it showed that also these spontaneous actions work in the right hands, of course. So thank you, Radek. It was great. Yeah. And what do we do? Again, I would like now really ask the audience to ask your questions. Really use the time to the fullest, and don't be afraid. Ask your questions. As you know, there are no stupid questions. There are only stupid answers. So don't worry. We don't mention your name if you like, but ask your questions. We'll be happy to answer. We know we would like to explore how you think and accommodate our development to it. So I'm taking back the presentation. I hope you could see my screen soon.
Yes, you can see it.
I was just playing with with a simple tutorial. So now it's definitely going to be the Q&A session. So before we will see your questions, we already see a few, but we would be definitely happy for more. I would go back to our website and show you that we have just disabled the annoying window with chatbot, which popped up, which has popped up all the time when you clicked anything. So as you can see, it's not coming anymore, and the icon is CFD support blue. So another improvement, right? Live during the webinar.
To prove how we are flexible, right?
Yeah. It was not very difficult, by the way. But anyway, let's get to it. So questions. I see a few. Yeah, that's great. That's great. So our friend Gabriel from Canada is asking whether we use on the machine, do you add fluid layer? So he's asking if we add fluid layer. I hope I understand. Typically, some people call it boundary layer, but in fact, it's the inflation layer of the mesh, right? It's the dancing meshes in the direction perpendicular to the surface, close to the surface, which allows to catch the boundary layer gradient or velocity gradient better. Definitely, yes, it's possible. I don't know. Maybe I could show this to give to give a little break to Radek, because he spent so much time with speaking. So I have a very simple tutorial here, which is our famous pipe. Very simple tutorial. I can click here. I want to see the mesh, and hopefully we have it there, which is, it's this mesh. And if I click at it and visualize the visualize the mesh, you can see that there are somehow thin layer of meshes close to the surface, and you can do it in the mesh settings, in the table of patches, which is the most important, the most critical part of the meshing, of course. And you say here that you want to see, for example, at the pipe wall, you want to see 3 boundary layers, or their layers, we call them inflation layers, which have their options in the layer meshing parameters. You can set the expansion ratio, or whether the fine layer is ratio of what, or whether it's relative or absolute. So you can play enough with the inflation layers for every rigid wall, or for every rigid surface. So hopefully this is the answer to the question. Radek, can you see a question you would like to answer?
Yeah. There are many of them.
That's great.
So, for example, the additional question from Gabriel. So, between each element, are you using an AMI? Which kind? So, we use the standard AMI approach. So this is the approach where you simply map the conditions from or the values, the variables from one side to another side. So I don't know which, if there are which kind, maybe I don't understand which kind, but it's standard mapping or non-mapping. It's interpolation from one side to another side. Is basically face-to-face or point-to-point mapping or interpolation from one side. So it's basically, it's similar like the frozen rotor, which is known from CFX, right? So this is standard AMI approach. And about the boundary conditions, what is an vent outlet? Maybe if I can share my screen just to quickly answer this question. So Luboš, can I?
Yeah. Sorry. Yeah. Are we switching? So I was reading something.
Yeah, no problem.
So are we switching over to you right now?
Yes.
Okay. I'll do it. Yeah.
Okay, show my screen, perfect. And when I borrow the TCAE training PDF, which you can find on our web pages. So here is the outlet vent boundary condition, which set it's like the modification of the static pressure at the outlet, which is not set directly by the pressure condition, but via the residual. And basically, depending on the velocity at the outlet and the value of the resistance, it sets the static pressure at the outlet. So it can more effectively catch the now I'm not sure if the search line, right? The last point with the stable conditions for the compressor. So this is more, we found it more applicable to this kind of simulation where you would like to go to the lowest possible flow rate for the compressor. We also use it for the fans. So it basically works like described here in this slide.
Yes. So what else? So
maybe there was one additional question, if I can answer.
Yeah.
I just, okay, let me just reopen it. Yeah, but Zachary question. So why I have exported the STS from Salome in this way? So the question is why I first triangulate the surface and then I export it, and why I not exported it directly from the Salome. So the point is that you need to have the watertight geometry. So it means you would like to have the triangulation of your geometry to be watertight. And the thing is, when you export each part separately, so for example, if you first I export the outlet, then I export the hub, so it may happen, and let me check if this happened. So let me open. I know it's working here. No, it's not connected. So let me open another view here. The basic is that typically the direct export to STL is badly manageable. So you don't have the options to set the parameters of the triangulation and to play with the topology of the triangulation. So let me get rid of this and let me open these generated STLs. So let me quickly go, here, STLs. So if I open, for example, the outlet and the hub, which I have generated, sorry, I have no display button. Sorry, I opened wrong view. So let me go back. Where is my, okay. I just want to have the plain paraview just to open it. Where is it? Sorry, I have several installations here. Okay, so I wanted just, just a plain paraview. And now I will go back, STLs, so hub and outlet, just to show you. So this is the export when I use the triangulation. So the topology is like this. You can see that all the triangles fits to the neighbor triangle. There are no holes. Everything fits perfectly. And now let me try if I export. So you can do the export directly from the Salome file, export STL, which I did. And when I open it, so this direct export. So let me open these two shapes. I will create a group just to see both of them. Surface with edges. So it behaves like this. You can see that, for example, it's nicely seen. So I was lucky. You can see there is a hole because the triangulation is done separately for each exported part. So we have no influence on the topology of the triangulation. And here you can see, because each part was exported separately. So here are some kind of big triangles, smaller triangles, and both of them are not topologically the same, which creates such a holes, which can bring problems to the meshing, because then basically the input STLs are not perfect. There are some kind of holes, and it can cause some trouble with the meshing part. Therefore, I do the first triangulation numerically, and then I export this triangulation as the STLs. So this was this is the reason why I did it in this way.
Yeah. So next question is, the question that there was, can you show the report again, because there were some curves. So Gabriel is asking whether what are simulations, what is what. So if you show some characteristic at the top of the report, I guess.
Yes. So
every point is one simulation. So you can say the line is, we call it speed line, right? It's rotating speed, and a set of boundary conditions is one simulation, which is represented by a single point in this view. You can see. So at the end of the day, you simulate quite, especially in turbomachinery field, you simulate quite. You never simulate just one point, or very rarely. You typically simulate a characteristic which is a speed line, one rotating speed, and several and set of boundary conditions which lead to several points that create the characteristics. So that's this. Also, there's a question about
maybe just let me add that all these points are run within the single simulation. So every next point is initialized by the previous point, which speed up the convergence. So it looks like, let's say, 18 different simulation, but inside it is run as a single simulation with jumping from one point as a result to initialize the next point. So which speed up the whole process. And it is a result on one click simulation. Yeah. So I just would like to add this information.
Yeah. And we have a couple of, I guess, quick questions. So what are we using, or are you using, what was the software using for FEA? So yes, it's important to say that for FEA, it uses, it's a weak connection between the fluid, I would say, forces acting on the surface and the FEA simulation of the structure. So it's the weak connection. So it means the most typically we export the forces, and actually the pressure is recomputed, the surface pressure is recomputed to the forces, and the forces are prescribed as a boundary condition for the FEA analysis of the structure. For the FEA is used Calculix, another open source pack, and it's one-way connection. That means a weak connection. The information of the deformed, if the structure is deformed, the information does not go back to the fluid. So it's this. Also, there's a question about Y plus. Yeah. So the theory is when you use the Wall functions, which is a simplification for steady state simulations, you can use Wall functions. It saves you a lot of simulation time. The typical Y plus is where the law of the wall is in charge, which is in between 30 and 300, for example. That's theory. And the alternative to using wall functions is to use like fully resolved mesh to the wall, where the Y plus is about in the order of just 1. So, but it's this. The software is ready, definitely completely ready for that, and it's up to the user what size of the mesh and Y plus is used. It's relatively straightforward to set everything. And also, yeah, an important question, or I find this question important. Again, Gabriel is asking whether the open form case can be pulled of the case of the TCAE case. Yes, definitely it can. So everything is extremely transparent. So everything is written down very, very similarly to what is OpenFOAM doing. So there's a certain structure in the project, and down there in the structure you can find the exact OpenFOAM case which can be run or maybe with some minor changes. It can be run with standard OpenFOAM. So TCAE is carrying with itself the complete OpenFOAM with everything, with all the tutorials and everything, and it's using its engine, and there are new or custom libraries and solvers, applications, function objects. We did, but on top of that, there's also complete OpenFOAM, and the case structure is standard, very standard. Okay. I think maybe this could be it. I can't see any other special questions we would like to answer here. So Radek, what do you think?
Yeah, let's conclude. I think we are more than an hour long, so I think it's time to conclude.
Yeah. But I'm happy. I still see that a lot of people is following still. So
Great.
that's great. That's great. So this is me again, and what do we do? Yeah, it's the Q&A session. So Radek, maybe we can show
Okay,
ourselves back, because
again.
this is the real end of everything. Hello, hello, hello,
Still here.
everyone, and also goodbye. This has been it. Very important point is we would like to ask you to get involved, get in touch with us. We will always be happy to answer all your questions. So feel free to ask your questions, and yeah, that's great. So we will come up with something. We have solution for everyone. So just looking forward to work with you.
Yeah, have a smooth and fast convergence. Yeah.
Yes,
Thank you for
all of
watching.
us. Yes, we all need it. Yeah. So we leave you with that. So thank you, everyone. Thank you, and bye bye for now.
Thank you. Thank you.
Thank
Bye
you.
bye. Take care.
Bye bye.